What makes a PID controller unstable in control systems? Imagine trying to balance a broomstick on your hand. If you push too hard or react too slowly, it falls. The same idea applies to a PID controller in a control system. A PID controller can become unstable mainly because of how its parameters are set. The proportional, integral, and derivative gains all influence how the system responds. If these gains are not tuned properly, the system can start to oscillate or even diverge. One common cause is when the proportional gain is too high. This makes the controller react very aggressively to errors. Instead of correcting smoothly, it overcompensates, causing the output to swing wildly. Think of it like trying to steer a car with a very sensitive steering wheel. Small turns cause big movements. The integral gain can also cause instability if it is too large. The integral part sums up past errors to eliminate steady errors, but if it is too aggressive, it can lead to what's called integral windup. This makes the controller output overshoot and oscillate because it keeps adding correction even when it is no longer needed. Plus, if the actuator reaches its physical limits, it saturates, which can make the system behave unpredictably. The derivative gain is meant to predict future errors and smooth out the response. But if it is set too high, it amplifies noise in the measurements. This noise can cause the controller to react erratically, leading to unstable oscillations. Another factor is time delays or phase lag in the system. When there is a delay in sensing or actuation, it causes the feedback loop to lag behind the actual process. If this lag approaches a phase shift of 180 degrees at a high enough gain, the system can start to oscillate uncontrollably. Improper tuning methods can also push the system into instability. Using rules that don't match the specific process dynamics or making small changes without testing can cause the system to become unstable. Physical nonlinearities, like actuator saturation, can also destabilize the system if not handled properly. When the actuator hits its limits, it introduces nonlinear behavior that can cause oscillations or divergence. In electrical control systems, the gains relate to voltage signals. If these are set incorrectly, the controlled variable like temperature or pressure can overshoot or oscillate beyond stable limits. Engineers analyze stability using transfer functions in the Laplace domain and tools like the Nyquist stability criterion. These help predict whether the system will remain stable with certain gain settings. Designing a stable PID controller involves careful tuning of the three gains. Techniques like the Ziegler-Nichols or Cohen-Kuhn methods give starting points, but adjustments are often needed for changing conditions. Filtering the derivative term and adding anti-windup schemes help prevent instability caused by noise and actuator saturation. In the end, stability depends on balancing responsiveness with damping. Proper tuning, considering delays, noise, and physical limits, keeps the system running smoothly without oscillations or divergence.